Hi everybody, this is Dr. Nigro with another screencast from our Newton's third law momentum unit. This one's going to look at inelastic collisions and the calculations that go along with those. All right, so the first thing we should do is define what an inelastic collision is so that you can recognize them when you read problems. All right, so the first thing to keep in mind, all right, as always, we've got two objects, all right, and they're going to come into contact. And of those two objects, one or both are in motion. All right, so unlike our recoil where both objects are still initially, in this case, one or both must be moving. That should be a 1, okay? The second clue that it is an inelastic collision is that after the collision, the objects move together. All right, and what does that mean that they move together? All right, so think about a car accident. If two cars collide and they get tangled up, so the metal impacts each other and they get kind of connected, all right, that would be considered an inelastic collision. All right, we'll talk about elastic collisions later, but in that case, they kind of just bounce off of each other. All right, so if you read a problem and it says that after colliding, the objects get tangled up or they move together, then you know that you have an inelastic collision. All right, another thing to keep in mind when we talk about inelastic collisions is there's always a loss of energy somewhere. It's usually in the sound, or maybe there's some heat released, or there's some sort of, crack. All right, but we're going to lose a little bit of energy when an inelastic collision is occurring. All right, so let's look at situation 1. All right, it's going to be similar to recoil. We've got two carts, A and B, and they're sitting on a frictionless track. Each cart has a mass of 1 kilogram, and cart A is moving with a velocity of 2 meters per second and collides and sticks to cart B, which is initially at rest. So cart A is moving, cart B is at rest, and we're going to say this is to the right, just to give us a direction. What is the final velocity of the two carts moving together? All right, so in this case, we're not going to just be proving conservation of momentum like we did with our recoil example. We're actually going to be solving for an unknown. All right, so we're going to do something similar to what we did before with recoil. We're going to draw some diagrams. All right, so I've got cart A, and it's moving to the right at 2 meters per second. All right, and then we've got cart B that is not moving. All right, so if we come over to our momentum boxes, all right, we're going to do the same thing we did before. This is our before situation. So V of A and M of A, we have a mass of 1 kilogram and a velocity of 2 meters per second. So if we multiply those, we're going to get momentum at 2 kilograms times meters per second. All right, we move over to cart B. We've got a mass of 1 kilogram, and the velocity for cart B is 0 because it's not moving, which means the momentum of B is also 0. All right, for our total momentum, we add them up, A plus B, and we're going to find the total momentum before the collision is 2 kilograms times meters per second. All right, now we're going to see what happens afterwards. All right, we're not really sure, to be honest. The only thing I know for sure is that A is now kind of tangled up with B, right? But I don't know what speed it's moving, and I do not know what direction it is going in. All right, so this time when we look at the after situation, all right, we really are considering these two things at the same time. Hold on, I need white. There we go. So I want to get rid of this line. All right, because really now it's A and B. So if we're talking about this particular situation, we need to think about it in terms of mass of AB and velocity of AB, because they're now one entity. All right, so for the mass of AB, I just add my two masses. So 1 kilogram plus 1 kilogram. So our total mass here is 2 kilograms. And then our velocity value is our unknown. All right, so the total momentum here is just the momentum of this single object. All right, so it's going to be equal to 2 kilograms times the velocity of that object. All right, now due to conservation of momentum, these two numbers, the before and the after, must equal each other. All right, so I can go down into my conservation of momentum box and I can set those two things equal to each other. A 2 kilogram times meters per second for my total momentum before has to equal my 2 kilograms times my unknown velocity of AB, which is the momentum after. All right, and if I rearrange, I find that the velocity of that combo unit afterwards is going to be equal to 1 meter per second. So there's my answer. All right, now formula. All right, we know that it's P before equals P after. And if we think about what we did mathematically up at the top, what we really said was the mass of A times the velocity of A plus the mass of B times the velocity of B. All right, so this is our momentum before has to equal the mass of AB, whoops, not plus, sorry about that, times the velocity of AB. And this is going to be our momentum after. So when we're talking about an inelastic collision, this is our handy formula. The two separately have to be equal to the two together, okay? All right, so let's put that to work. We're going to come down here and look at situation number 2. All right, we have two carts. Again, same mass values. Cart A is moving with a velocity of 2 meters per second, collides and sticks to cart B, which is also initially moving with a speed of 1 meters per second. All right, because these velocity values are positive, we're going to say that both carts are initially moving to the right. All right, so here is cart A at 2 meters per second to the right, and here is cart B at 1 meter per second to the right. All right, so we come over here, set up our momentum, whoops, let me fix that. Set up our momentum chart. All right, so we've got a mass of A of 1 kilogram, velocity A of 2 meters per second, which gives us an initial momentum of 2 kilograms times meters per second. For cart B, we've got a mass of 1 kilogram, and then we've got a velocity of 1 meter per second, which is going to give us a momentum for B of 1 kilogram times meters per second. All right, our total momentum is A plus B, and so we end up with 3 kilograms times a meter per second. All right, now afterwards, the two carts collide, so A collides with B, and I use that squiggle line to show they're moving together. All right, and I'm going to assume they're moving in this direction, but we'll see. They should be. All right, so we do the same thing that we did before. All right, we're going to treat this instead of as two separate entities. Oops, I'm going to get rid of this line. All right, and we're going to treat this as one thing. This is going to be AB. So the mass of AB is the sum of the two, so that's 2 kilograms. And the velocity of AB is our unknown, all right? So the total momentum is just going to be the momentum of AB, which is going to be 2 kilograms times our velocity. All right, so because the before has to equal the after, our 3 kilograms times meters per second, which is our initial or our before momentum, has to be equal to 2 kilograms times that unknown velocity of AB. All right, so if we solve everything, V of AB is going to be equal to 1.5 meters per second. All right, so once they collide, they'll be moving together in the same direction at 1.5 meters per second. So a little bit faster than B was going, but a little bit slower than A. All right, so again, this particular problem, we could have solved it just using the formula above, right? I could have said mass of A, which is 1 kilogram, times velocity of A at 2 meters per second, plus mass of B at 1 kilogram times its velocity at 1 meters per second has to be equal to the mass of the two, which is 2 kilograms, times that unknown velocity, all right? So you don't have to do it this way. It's just a nice way to break it down so you can see it. All right, but if we do all of the math here, we're going to end up with a velocity value of 1.5 meters per second, just like we saw over here. Okay? All right, so again, remember, if it is inelastic, the two objects have to be moving together at the end. We didn't do any examples where we had one of the initial objects moving towards the other, but that could happen too. And if that case happens, you're going to need to put a negative sign with that velocity value. So just make sure you are paying attention to your signs, okay? All right, come back for our elastic look in the next screencast.